Hello, today we're going to be doing a quick overview of the 12 basic functions, what their graphs looks like, and how you might represent them mathematically. Let's jump into it. First off, we have the identity function. It is represented by the equation y is equal to x, and its graph looks like just a continuous line going from right to left, down to up, infinitely continuously. Next up, we have the quadratic function. Its parent function is represented by the equation y is equal to x squared, and it looks like a big parabola, a big curve, with the two ends going off infinitely in one direction and a vertex in the other. Our third equation is the cubic function. It is represented by the equation y is equal to x cubed, and its graph is represented by this weird squiggle curve with its endpoints facing in different directions, and it has a point of inflection in the middle. Up next is the rational function. It is represented by the equation y is equal to 1 over x. We can see here that the rational function is our first function with asymptotes. In fact, it has two asymptotes, a vertical asymptote and a horizontal asymptote, with the parts of the graph being on either side, in this case being in the bottom left corner and the top right corner. Up next, we have the square root function. This function is not continuous, being only going off infinitely in one direction but not the other. It is represented by the equation y is equal to square root x, and its graph looks like this. Up next, we have the absolute value function. It's represented by the equation of y is equal to absolute value of x. That's what these bars mean. Its graph looks like a big V, making sure that the parent function, all the values are above the x-axis, since you want all the values to be positive, all the y values to be positive. Up next, we have the sine function. It is represented by the equation y is equal to sine x. Its graph looks like this big wavy curve, and it actually looks very similar to another function, the cosine function. But the only way you can really differentiate between the two functions is by looking at the center. The sine function will have a point at 0, 0, or at least the parent sine function, whereas the cosine function will not have a point at 0, 0. This brings us up to the cosine function. Here we have the cosine function represented by the parent function equation y is equal to cosine x. And as we can see, the cosine function looks very similar to the sine function, just looking like a big squiggly wave. Except if we look at the origin, you can see that the cosine function does not intercept the origin at all, instead crossing the y-axis at the point 0, 1. Up next, we have the exponential function. Its parent function and its most common variant that you'll see is y is equal to e to the power of x. This is another function that you can see has an asymptote, this time just a horizontal asymptote and no vertical asymptote. We can see that its left end behavior adheres to the asymptote, while the right end behavior goes off to infinity. Next, we have the logarithmic function. It's the inverse of the exponential function. So this function will only have a vertical asymptote instead of a horizontal asymptote. We can see that similarly to the exponential function, only the left end behavior really follows an asymptotic behavior, whereas the right end of the function, or the right end behavior, will follow, will go off into infinity. Here you can see the two most common ways that the logarithmic function is expressed, through the natural log, ln, and the base 10 log of just represented by the word log, x. These functions, if you graph them, will look very similar, but yet they have different properties of growth. Next up, we have the logistic function, a little bit more complicated function that we've been through, but it is still very manageable. This logistic function has two asymptotes, two horizontal asymptotes in fact. one at y is equal to 0 and another at y is equal to 1. These two horizontal asymptotes create a bound end behavior where the logistic function will not go below 0 or above 1. And it is represented by the equation y is equal to 1 over 1 minus e to the power of negative x. Last but not least, we have the greatest integer function. It's not a very common function that you will see in mathematics. It has more applications in computer science than mathematics or pure mathematics, but it is still interesting to know about. It is represented by the equation y is equal to integer x, and this graph looks like this, with a bunch of disconnected lines with empty dots here representing the lack of a point here, and full dots here where you will see there is a point there. Despite its look, the greatest integer function will have a continuous domain, yet discontinuous range.